In this lecture, we will discuss energy density and the Poynting theorem. This discussion concerns what would be the equivalent of the work energy theorem for electrodynamics. Okay, what are the prerequisites we should know? First, we know that energy is conserved. This is much like charge. In the context of electric charge, though, we could capture this in a mathematical statement in which we considered the charge density, which is a function of position and time, the derivative of this quantity with respect to time, plus the divergence of the accompanying current density, that is the vector j. The sum of these two terms was equal to 0. We gave this equation a name. This was the so-called continuity equation. And this essentially is a statement of the conservation of electric charge. Next, we of course know Maxwell's 4 equations. For the case of free space, let's recall them. First, the Gauss Law for the electric fields, div E is rho divided by epsilon naught. The corresponding equation for magnetic fields, the divergence of B, which is always 0. Then next, the curl of the electric field. The electric fields, of course, are a function of space and time. This is equal to the negative of the time derivative of the field B, which also depends on space and time, and the curl of the magnetic field B, which is equal to mu naught times J plus the Maxwell term epsilon naught mu naught, the time derivative of the electric field. Since this discussion is about the work energy theorem, the electromagnetic field that we are considering here, the fields E of RT and B of RT, these do work on a system of charges. So there is a force, an electromagnetic force, which is acting on a system of charges. For an individual little charge q, the force acting on it due to the fields A and B is the Lorentz force, which is equal to q times E plus V cross B, where V is the instantaneous velocity of the charge q. Okay, now we are in a position to talk about the details of work and energy in the case of electrodynamics, right? So since we know what the force acting on a charge q is due to electric and magnetic fields E and B, we can consider a more general scenario. We can consider a system of charges which is located within a volume V, and let's say within this volume I consider an infinitesimal element with a volume dV. The charge density of this volume is described by the scalar function rho of RT. Therefore, now infinitesimal element dV contains a charge which is rho times dV. The work done on this elemental charge by the electromagnetic field is of course given by this Lorentz force law. I'd like to ask the question, what is the rate at which the fields do work on this little charge q? If in a time interval dt, this charge element is displaced by an amount dl from its initial to final location, and the work done in this causing this displacement is essentially equal to f dot dl, which is here equal to QE plus V cross B, the force, dotted with the quantity dl, right? But then dl is related to the instantaneous velocity of the charge v over this time interval as v times dt. dt of course is a scalar. Therefore, f dot dl is q times E plus V cross B dot V dt. Now, the left hand side is the amount of work done by this force in a time duration dt. Therefore, the rate at which work is done, that is dw by dt, is essentially equal to QE plus V cross B dotted with V. We can now consider the term Q times V cross B dotted with V and permute these symbols V and B cyclically within the cross and dot products as we are allowed to do, and this quantity of course turns out to be 0. But this is just a statement of what we already know very well, that magnetic fields do not do any work on charges, right? So now coming back to the rate at which work is done on these charges, this is now nothing but QE dotted with V. Now let's recall that Q is the charge of that infinitesimal element within a big bulk charge distribution which was characterized by the function rho. So Q essentially is the charge contained in this, and this is rho times dV. There are two V's in this derivation, so one should be careful in writing them. So d work by dt is nothing in this case but rho dV multiplying E dot V, or this is E dot rho V multiplying dV. And once again we have to recall that J, the current density vector, is given by nothing but rho times V. Rho, of course, is a function of space and time. As a consequence, we now have a nice relationship between the work done on this charge and the electric field E and the current density vector J for the case of this infinitesimal element dV, or the total rate at which work is done by the field on this entire distribution. This is given by integrating this quantity over the entire volume V, with E dot J being the integrand. Okay, so this is a good stopping point. This is an important result that we have derived. The rest of the discussion is based on this. So this is how much work the electric and magnetic fields do on this volume, which has a charge distribution rho. I would like to express the quantity E dot J in terms of entirely the electric and magnetic field. Maybe this is possible. Let's try this out. If so, it would be nice in the sense that I can then write down an equation between the work done on the charges in this entire volume V and the electric and magnetic fields which are involved in this process. So let's now make use of Maxwell's equations. We had the Maxwell equation for which involved J, which was the equation involving the curl of B. This was equal to mu naught J plus mu naught epsilon naught dE dt. Okay, now the quantity that we seek is E dot J. This is what we are seeking. Therefore, let's express J, the quantity that we are seeking to eliminate here, as a function of the other variables in the Maxwell equation. This is curl of B by mu naught minus epsilon naught d dt of E. Or now E dot J is E dot curl B minus epsilon naught E dot d dt. Once again, now let's recall the following product rule. The divergence of the cross product of two vector fields, in this case E and B, can be written as B times the curl of E minus E times the curl of B. So we now write this entire thing down. So let's take also further this term, recalling Faraday's law, which is of course a Maxwell equation, where curl E was equal to minus d dt of B. So we can substitute for this. B dot curl E, this is minus B dot dB by dt. Now we have two terms over here, and we can substitute for these terms in the equation we have written down for E dot J. But before that, we can simplify terms of the type B dot dB by dt as equal to 1/2 the derivative of B square, the square of the magnitude of the magnetic field, and likewise E dot d by dt is half the time derivative of E square. Okay, now after having deduced all the tools that we need to write down E dot J in terms of entirely the fields E and B, let's recap that we had simplified E dot J to be 1 over mu naught E dot curl B minus epsilon naught multiplying E dot d by dt. But then this is nothing but plugging in the first simplification, 1/2 epsilon naught d dt of the square of the magnitude of the electric field vector. And then we can now go for the other simplifications. That is, we use the expression for the divergence of E cross B, which turned out to be equal to, in this case, minus dB dot dt. This is actually equivalent to the term B dot curl E minus E dot curl B. But what we want to substitute for in this equation is essentially E dot curl B. This is the term. So let's write the rest of this equation over here in terms of having E dot curl B. E dot curl B is therefore equal to minus B dot dB by dt minus the divergence of E cross B, or this is nothing but negative 1/2 d dt of B square minus the divergence of E cross B, so that E dot J becomes minus 1 over mu naught divergence of A cross B minus 1 over 2 mu naught dB square by dt minus 1/2 of epsilon naught ddt of E square. This is really the equation that we were looking for. Which I can now write down very nicely as follows. This is minus 1 over mu naught, the divergence of E cross B, minus 1/2 of the time derivative of half epsilon naught E square plus a half 1 over mu naught B square. Now we recognize that the quantity 1/2 epsilon naught E square is the energy density of the electric part of the EM field, and likewise the quantity 1/2 of 1 over mu naught B square is the energy density of the magnetic part. Right? Therefore, I now have a very powerful result by recognizing that the rate at which work was done by the field on this entire system of charges in the volume V with local charge density rho is equal to minus d dt of the following quantity, which is 1/2 epsilon naught E square plus mu naught B square integrated over the volume minus 1 over mu naught the integral over the divergence of E cross B integrated over the volume V. Now let us define a new vector field S, which is a function of space and time, as follows. This is 1 over mu naught E cross B, both of which are functions of space and time. Then we have a very nice expression for the rate at which work is done. This is again the time derivative of the energy content in the fields themselves and the integral over the divergence of this new vector field S, which we have defined over this entire volume. Right? Now we can use the divergence theorem and write this quantity, the integral over the volume of the divergence of S, as nothing but S dot dA integrated over the surface S with the relationship between the surface S and the volume V being that the surface S encloses the volume V. So the rate at which work is done is essentially the time derivative of what I would now call W, the energy density in the fields, minus the flux of this new field S calculated over the surface S, which envelopes the volume V. Using the symbol S for both is a bit unfortunate, but we can live with that. But this is an important result in that this is the work energy theorem of electrodynamics. It's called the Poynting Theorem. And the vector field S defined as 1 over mu naught E cross B, or equivalently just as E cross H, since for vacuum B is mu naught H. This vector field, of course, is very appropriately called the Poynting vector field, or very simply the famous Poynting vector. Now we should be able to interpret the Poynting vector. The Poynting vector S is nothing but the energy flux density, and the Poynting theorem itself says the following. In words, the Poynting theorem says that the rate at which the EM fields do work on the system of charges rho, which is contained in the volume V, is equal to the rate of change of the energy density of the fields themselves less the flux of energy leaving the volume containing these charges. Okay, so on one side of this equation I have work, on the other side I have energies or the energy densities involved and their flux. Therefore, this is the work energy statement for EM fields. Alright. There is also another way of looking at this equation. Let's write this in the differential form. So-called d work by dt is now equal to the time rate of change of the energy densities of the field, where little w is WE plus WB, that is the electric plus the magnetic energy densities, plus now the divergence of S. So the rate at which work is done is essentially equal to this quantity on the right with negative sign, essentially coming out of convention, in that if the fields do work on the charges, then this quantity turns out to be negative. To understand this even better, let's consider the same volume V, and let's remove now all the charges from this volume, right? Then let's see what happens to this equation. Then the left hand side, d work by dt, we calculated was just E dot j, and this essentially is E dot rho v by the definition, and this is equal to 0. So if there are no charges to work on, we have time rate of change of energy density plus divergence of the Poynting vector is equal to 0. Compare this now to the equation which stated the conservation of charge, d rho by dt plus the divergence of J is equal to 0. These two are therefore statements of the local conservation of energy in the top case and charge in the case of the equation in gray, right? So this is really the significance of the Poynting theorem. The Poynting vector plays an important role in electromagnetism. We can now also see that the vectors E, we can also see that the vectors E, the vector H or B, and the vector S form a right-handed triad. S essentially is the vector field which captures everything that is known about the transport of energy, both in magnitude and direction. In other words, if I have an electromagnetic wave propagating, then energy is conveyed in the direction which is perpendicular to E and B mutually. This is something we have learnt also in earlier education, that electromagnetic waves are transverse waves. Now we know that energy transport is essentially happening in the direction perpendicular mutually to E and B, which is also, as we will learn in a different unit, the direction of propagation, which is captured by the so-called K vector. So this is an important part of the edifice of electromagnetic theory. The fields also have a momentum density, and the momentum density essentially is given by mu naught epsilon naught multiplying S, which is a function of RT, or it is simply epsilon naught multiplying E cross B. With that, we will close this session, and in forthcoming ones look at problems involving the Poynting vector.